Welcome to ENET 140, Operational Amplifiers at Bellingham Technical College. This is the first recorded lecture in our class on op amps, and we'll be drawing material for this brief lecture from Chapter 1 of our James Fiore Operational Amplifiers textbook. So what you're seeing is my hand notes on the material that is in your textbook, and it goes over the main points that I expect you to gather and that you will need to be able to describe gain in operational amplifiers. So the subject of our lecture is decibel gain, and you're probably familiar, I hope, with gain from your study of just normal amplifiers, particularly bipolar junction transistor styled amplifiers in various common configurations, common base, common emitter. One of the characteristics of those different configurations was how much voltage and current gain you could obtain from the circuit, from the amplifier circuit. And in each of those cases, we describe gain as a simple ratio. It was voltage out divided by voltage in, or current out divided by current in, and quite often we would offset one versus the other. We'd have high voltage gain, low current gain, or vice versa for different configurations. So we're going to take a step back and we're going to discuss gain more generally, and we're going to discuss a very handy mathematical way of expressing gain known as the decibel scale. The decibel scale is probably something you're familiar with in terms of sound perception. And in fact, it's used all the time for hearing impairment and for noise abatement and mitigation for things like highways and industrial equipment. And basically, one of the ways that decibels are used in common English is for the power associated with the compression wave of sound and its recognition signaling in the human ear and brain. So our brains are sensitive to power transmitted from a sound wave, which is a compression wave in the air. And we respond to it based on the log of the power of that compression wave. So that's why you often hear in hearing protection warnings, if you work in an industrial workplace, which you should very much pay attention to, that a decibel scale is logarithmic. So something that only is a couple of decibels higher has a lot more power of that sound. So it's a caution that we should all pay attention to as safety. Well, the same thing goes with gain. Quite often we're going to be looking with operational amplifiers of huge ranges of gain, going from no gain, just unity gain, or even an attenuation, maybe negative gain, gain less than 1 on a ratio, to something several orders of magnitude higher. Quite often the circuits we'll be looking at are going to vary their gain with frequency input. So the same circuit will give a vastly different gain depending on what the frequency of our input signal is. So we need a way of expressing gain over huge spans of orders of magnitude changes. And that's what the decibel scale is great for. It is a log base 10 scale. So power in a sound wave, gain in a circuit. We're going to express them both with what's known as the decibel scale. So two flavors of decibel gain that we'll deal with in op amps. One is decibel power, and the other is voltage gains expressed on a decibel scale, either as a voltage ratio gain or as a given voltage reference to a single stated reference signal. So it isn't always a ratio of in and out. It could be a ratio of voltage of interest to a reference. So what's the definition of decibel power? And we'll start with power because that's really the reference, and it's why I started with the example of the power of a sound compression wave and perception in the human ear. When you hear decibel, think power. Unless otherwise noted, decibels always refer to a ratio in some kind of power. And if we use it for voltage or current, for instance, we're going to use the same power expression and then literally insert Joule's law, P equals IV, or P equals V squared over R, and then we're going to modify that power equation a little bit using properties of logarithms and derive an equation for voltage ratio for equivalent power. So this is a little bit like RMS, where it was equivalent power. And this should be looking an awful lot like half power frequencies that you may have looked at in resonance. So decibel gain is primarily intended to convey some measure of how much power we're increasing or decreasing with our circuit. So before we get into decibels, in other words 1/10 of a bell, we can start with a bell gain, and that's BEL. This is somebody's name. Here's the definition. It's the log base 10, so this is the logarithmic mathematical function operating on ordinary gain, which is our gain ratio. So ordinary gain, capital letter G, is just the power out divided by the power in. So power output over input. So we put that in for G, that's ordinary gain. So bell gain is just log base 10 of P out over P in. So power ratio. And remember, a logarithm can be expressed with any base. If you've used natural logs to solve for differential equations, maybe for an RC timing circuit, you used log base E or the natural log. Now we're using log base 10. So be careful if you're using your calculator to calculate this. You need to use these equations. If you're asked for a decibel or a bell gain, you need to use log base 10. So if you're reading along in Mr. Fiore's book, you'll notice that he uses the prime indicator to indicate that we're on the log scale expression for power, or a bell gain, as opposed to just an ordinary gain, which is just the ratio. So our bell gain is log base 10 of our ordinary gain. Okay? Well, if that's a bell, a decibel is 1/10 of it. So a decibel is 1/10 of a bell, so decibel gain is going to be expressed as 10 times log base 10 of ordinary gain, and we abbreviate that as little d and big B, so that stands for decibel. So that's it basically. Power out over power in, you take the log base 10 of that ratio, multiply by 10, and that's the equivalent decibel gain in power. So here's some, if you want to have some shortcuts, if you don't have your calculator out in the field with you and you are doing some comparisons of power, maybe you're working in the lab and you don't want to grab your calculator, handy things to note. Log base 10 of 2, so that would be a doubling in power, is approximately 0.3, and since the decibel equivalent of this would be 10 times log base 10 of 2, that means doubling your power is equivalent to a 3 decibel gain. And that's just because log base 10 of 2 is 0.3. Of course, we multiply by 10 to give us decibels, so it's 3. If we're halving the power, we're operating on 1/2, or 2 to the minus 1, and if you're familiar with properties of logarithms, that 2 to the minus 1 is equivalent to negative log base 10 of 2. So that would give us a negative 0.3, multiply by 10 to get the decibel level, and we're at negative 3. So if we have the power, that's a negative 3 decibel gain. So one of the things to remember about logarithms is it basically can turn multiplicative operations into additive operations. So this is something hopefully you studied in your mathematics, but we'll go over those important properties right here. So if you didn't, you will learn them now. Other important benchmarks, log base 10 of 10 is 1. Log base 10 of 100 is 2. So you can see that another way of expressing a log is the exponent that you would have to raise the base to get what's being operated on. So that is literally the definition of the logarithmic function. So log base 10 of 10 is 1 because you would have to raise 10 to the first power to get 10. Log base 10 of 100 is 2 because 2 is what you'd have to raise 10 to get 100. 100 squared, or excuse me, 10 squared is 100, or 10 times 10 is 100. So this is the general expression for log base 10, and so that would be basically what you have to raise, x is what you'd have to raise 10 to get what's in here, so that would be 10 to the x. So you can refer to this as in trying to remember what logs and anti-logs are. So that also tells you here that basically if you have to invert a log base 10 function, you just simply take whatever the argument is and raise 10 to that. And we'll have some examples of that a little bit later, taken straight out of Mr. Fiore's book. Okay, properties of the logarithm function that are very, very handy. And in fact, we use this one here to derive the expression for voltage gain expressed on the decibel scale. So again, hopefully this is a mathematics review for you all, but just in case, one of the rules for natural logs or log-based anything, is that if you have two numbers multiplied and you take a logarithm function of any base of that product, it's the same as summing the log of each of the two multipliers in the product and adding them together. So for our case, log base 10 of a times b is equal to log base 10 of a plus log base 10 of b. So that's really handy if you're trying to solve for, say, the decibel equivalent gain of a cascaded amplifier. So if you remember, if we basically take the output of one bipolar junction transistor amplifier and we apply it to the base of another, we're going to end up with a cascaded amplifier configuration, and so the gains will multiply. So we'll have beta of amplifier 1 times beta of amplifier 2. Well, if we wanted to get the equivalent decibel gain of that, we would end up with, if it was a BJT, we'd have beta 1 for A and beta 2 for B, and we would take the log of that. But we could also just say, okay, I could just express my first beta on the log scale, take the log of that, multiply by 10 and get a decibel gain, and just add that to the other. So if you're looking at ordinary gains, ratios, you would multiply them for a cascaded amplifier. But if you're expressing those same gains on the decibel scale, you'd add them for a cascaded amplifier. And of course, since division is just multiplication by something raised to the -1, we end up with just having a minus sign if we have two numbers that are a quotient. So the numerator will be here with a positive and the denominator negative. Now, the reason we get that negative sign is that a divided by b is really like saying a times b raised to the -1. And we can invoke this third super handy property of logarithmic functions that says, if I'm going to take a log mathematical function, I'm going to operate on something raised to a power. So here I've got a, which is a constant. It's any constant. It could be 3, 4, 5. It could be 10,000, representing the beta of an op amp. And I'm going to raise it to some power, whatever that is. I can rewrite that as that exponent multiplied. And this time I'm going to multiplying the log of just the function without an exponent. So basically the exponent can come down and be a multiplier in the front. And that's why we have a -1 up here. Because by being in the denominator, that b was really raised to a -1. So I separated a and b using this rule, and then I took that -1 exponent and I brought it down in front, which flipped the positive to a negative. So super handy. We're going to use this to express an equivalent decibel scale for voltage using our Joule's law of P equals I squared over R. And that too is going to come down in front, and we're going to have a different expression for decibel gain for voltage. In fact, here it is. So we're used to expressing gain in terms of voltage out over voltage in. How much higher of a peak am I going to have in my signal output? Maybe if you remember your AC load lines with amplifiers, you wanted to make sure that your Q point was such that the amplitude of your output signal wasn't going to get clipped. So we're used to output and gain being expressed in terms of a voltage ratio, not a power ratio. Well, as it turns out, if we want to express our voltage gain on the decibel scale, we have to do it in terms of equivalent power. So what we're really saying when we say decibel gain in terms of voltage is we're saying what would the equivalent power gain on the log scale be for a given voltage ratio. And to calculate that, all we do is invoke Joule's law and say, well, the power input to my amplifier is the input voltage squared over the resistance of the amplifier, and this would of course be its input impedance. Obviously, for this argument, we're going to assume input and output impedance are the same. That's not always the case, but it's well enough for the circuits that we're going to use. And so P out would just be V out over that same R. So if we can assume that, now we can write our power ordinary gain ratio in terms of power and just drop in our Joule's law expression for power out, which is V out squared over R, our Joule's law expression for power in, which is V in squared over R. The R's cancel and we're left with V out over V in squared. So that's our ordinary gain, our power out over power in, but expressed in terms of voltage, something that we're used to measuring, that we need to measure. Okay, let's just pop this ratio, which is the same as P out over P in, right into our expression for decibel gain, that G prime. So we're going to have 10 times log base 10 of P out over P in, and we're going to substitute our V out over V in squared. Oh, look at this. This is just like our A raised to the X, where 2 is X and V out over V in is A. So this 2 can come around down and multiply by our 10, and we get 20 times log base 10 of V out over V in. So this is decibel power gain, but expressed in terms of our output and input voltages, and we end up with a 20, not a 10, if we're using our voltage ratio. Okay, because it's really a power gain, but we just write it in terms of voltage, and the 20 is what basically makes them equivalent. So we used a nice handy property of logarithm functions. So if somebody says, hey, here's my output power versus my input power, you use the 10 log base 10 of the power ratios. If you are measuring your input and output signals on your oscilloscope, and you have V out over V in as a ratio based on peak or peak to peak or RMS, doesn't matter, you could have V out RMS over V in RMS. Same thing, you use the to express decibel gain, use the 20. So two different ways to get input in terms of a ratio to express gain on the decibel scale. Okay. Well, as it turns out, some people are so enamored of expressing things on this logarithmic decibel scale that they want to use it to express everything. They're kind of logarithm happy, I guess. So this is something that you will see in practice in the study of electronics, especially any time that there's a lot of amplification needed for something. So if we can express a voltage ratio on the decibel scale using this equation, we could also express a single voltage on using the same equation and just use some denominator that's a known reference. So say I wanted to express 10 volts on the decibel scale. You know, you might ask, well, wait a minute, you can't do that because this needs a voltage ratio. And what if I said, okay, fine, just assume V in on the denominator is 1 volt. So I'm going to express 10 volts in decibels with a 1 volt assumed reference. So I'd put 10 volts in for V out, I'd divide that by 1 volt for V in, so I'd have 20 log base 10 of 10 the volts would cancel as they need to do for the logarithm function to operate on it, and so basically log base 10 of 10 is 1. Since 1 is the number I would raise 10 to get 10, so I'd get 20. So that would be a 20 decibel gain equivalent, and that would be considered a dBV, or decibel voltage expression. So in other words, if you want to express any quantity on the decibel scale, pick a denominator for the ratio and reference that. So you'll see some people expressing voltage on the decibel scale, and they will always have to tell you what the reference is. Now, as far as that goes, we can express power just by itself on the decibel scale using that same kind of idea of a reference. It doesn't necessarily have to be the gain of a circuit. It usually is. But you could just express the power output of your space heater. Maybe you're using a space heater to keep your feet all toasty while you listen to this lecture. And you look at it and you could express the watts power output on the decibel scale by assuming some reference, probably of 1 watt. Maybe you have a 1,000-watt heater or a 100-watt heater. So you'd put 100 in the top for P, you'd divide by 1, so log base 10 of 100 would be 2, so you would have a 20 dBW heater, which is the same thing as 100 watts. So again, the W out front here, dBW, is telling you that your reference is 1 watt. A lot of times you may be working with low power output signaling electronics where we certainly hope we're not generating 100 watts of power. We'd melt our circuit. So we might be looking at things on what's called the dBm scale, and this is little m, and it stands for milli, as in the 1/1000th scale in the metric system. So in this case, the only difference is whatever power we're looking at is referenced to 1 milliwatt. So this is going to be a much bigger number because we're dividing by a very small number. But we have to remember that there's the reference. So the same power expressed in dBm is going to have a bigger number than that power expressed in dBW. But it's just what's on the denominator, and then when you create your ratio, remember you have to write all of these numbers out so the watts totally cancel. And so here's an expression of dBV. So that's it. Those are the rules. Probably the biggest thing to remember is when you start looking at voltage ratios and amplifiers and mixing up power outputs and voltage outputs, don't ever forget to multiply by your 20 when you're looking at voltage. And this would hold for current as well. If you were expressing your gain in terms of current gain, you would end up with a 20 for the same reason you did up here, because you'd be using that I squared times R. The R's would cancel. So regardless, if you're putting in power ratios, you end up with 10. If you're putting in voltage or current ratios, you end up with 20. And then if you're using the decibel scale to reference a single voltage, a single current, a single power, it is essential that you tell everyone what your reference is so they know what's on the denominator. And if somebody cites a power or a voltage or a current on the decibel scale and doesn't tell you their reference, ask for it. Don't assume, because it could be off by 3 orders of magnitude, which would be a bad mistake. Okay, that is it for decibel expression of power, voltage, and current. And so next up will be a few examples taken straight out of our Fiore Chapter 1 textbook to give you an idea of how that goes for some real problems.